Chem Exam Explained, where the aim is chemistry clarity, exam mastery. In this video, we will be looking at CAPE Chemistry 2023, Unit 2, Paper 2, Module 1. Let's begin. Module 1 is looking at the chemistry of carbon compounds. Question 1, Part A. Give the IUPAC name for the compound A, whose molecule is shown below. Now, if you look at the molecule, you will first count the number of carbon in the longest continuous chain. So it is obvious that there's only one continuous chain here. So you can start counting from the left. So you go 1, 2, 3, 4, 5, or the right, 1, 2, 3, 4, 5. So that is your parent chain. So the first thing to do is to identify the parent, which gives us pentane. Now you'll notice that there is a bromo group on the third carbon. So that would be our branch. So the parent is pentane and the branch is bromo. And the branch is on carbon number 3. Hence the name 3-bromopentane. It is very important to note that if you have two numbers, you must put a comma between the numbers. If you have a number, then a letter, then the hyphen must go between the number and the letter. Part B1. A hydrocarbon with molecular formula C6H14 is known to have 5 structural isomers. Draw the structures for each of these isomers in the space provided below. So let us go to a whiteboard and have a closer look at the molecule C6H14. Now, remember that if you are isomers, you must have the same molecular formula, but different structural formulae. Now, if you say the formula is C6H14, then it follows the general formula CnH2n plus 2, which is simply saying that this particular compound is an alkane. So C6H 2 times 6 plus 2 would be C6H12 plus 2, 14. Hence, alkane. So since our molecular formula is C6H14, let us start with the simplest isomer. 1, 2, 3, 4, 5, 6. We can then check the number of carbon to make sure it is correct. 1, 2, 3, 4, 5, 6. And the number of H's should also be correct. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now we could start the other isomer with a branch. So instead of going 6 carbons on my straight chain or my longest continuous chain, I will now go with 5. So 1, 2, 3, 4, 5, and then start with a branch. So I now have 6 carbons, 1, 2, 3, 4, 5, 6, and now I have 14 H's, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now you'll notice that this particular one here is hexane. All right. You could say N-hexane, but at this level, it's okay to just say hexane. Here, to name this one, we look to see which side the branch is closest. Is it closest to the left-hand side or closest to the right-hand side? You'll notice that it is closest to the right-hand side, so we'll start our numbering from this side. So that will be 1, 2, 3, 4, 5. So the parent is pentane, and the branch is a methyl branch on the second carbon. If the branch is a methyl branch on the second carbon, then the name becomes 2-methyl pentane. So that's our second isomer. Now the third isomer is the same parent, pentane, but I will now move my branch from number 2 carbon to the number 3 carbon. So I go 1, 2, 3, 4, 5, The branch is now on the third carbon. So you can count from any side because it is the same number of carbons from either sides. So the name would be 3-methyl pentane. Now that we are through with the pairing being pentane, we can go with a smaller number of carbons now, which is butane. 1, 2, 3, 4. And we could start with the branches on the second carbon and have 2 of them. So now I have 2 branches on the second carbon, counting from the right-hand side to the left. So that would be now 1, 2, 3, 4. So the carbon here is on the second carbon, which is on the parent. So it's now 2, 2 hyphen 2 of them, so dimethyl butane. And the other one, same parent, 1, 2, 3, 4, but now the branches are on different carbons. So now I have a branch on the second carbon and a branch on the third carbon, hence 2, 3 hyphen dimethyl butane. Now it's very important to note that when you have a number and a letter, you must put a hyphen between. When you have 2 numbers, the comma must go between the numbers. Very important in the name. So these are the isomers for C6H14. So based on what we just did, you'll see that we have part 1 here being hexane, then 2-methyl pentane, then 3-methyl pentane, then 2,2-dimethyl butane, then 2,3-dimethyl butane. And we answered the question for part 2. State the IUPAC names of any 2 isomer in B part 1. So you could choose any 2 of the 5 isomers that we just drew. Part C1. Write the IUPAC names of the geometrical isomers B and C shown below. Now, once you look at this particular structure for B and C, the structures for B and C, you'll notice that these are cis-trans isomers or geometric isomers. Now, when you have 2 same groups on the same side, the name is different from when you have 2 same groups on opposite sides. So the H's are the groups that are similar in B, and the same H's are the groups that are similar in C. But in B, the H's are on opposite sides of the carbon-carbon double bond, hence trans. While in C, the same groups, they're on the same side, hence cis. So the name you could give is trans-pent-2-ene or trans-2-pentene. And for C, cis-pent-2-ene or cis-2-pentene. Now for compound B, in C1, they reacted it with hydrogen bromide to yield the Markovnikov product. Now this is obviously a mistake because when you form the product by reacting compound B with HBr, you do not produce a Markovnikov product. Okay, so this is a mistake on the part of the examiners. The Markovnikov rule does not apply in this case. This is only an electrophilic addition reaction. All right. So in this case, you'll see that I wrote the reaction. You'll notice that Br is being added to the second carbon, which is the first carbon in the carbon-carbon double bond, and H is being added to the third carbon in the compound, which is the second carbon in the carbon-carbon double bond. Now, why did I do it this way? Why didn't I put the Br on the other carbon and the H on the other carbon? If I did that, then I would not produce a compound that is an optical isomer, or I would not produce a chiral carbon. So the best thing to produce a chiral carbon is to put the Br on the second carbon, which is the first carbon in the carbon-carbon double bond, and the H on the third carbon, which is the second carbon in the carbon-carbon double bond, and I now produce 4 different groups, which makes my carbon a chiral carbon. And if I now have a carbon that is a chiral carbon, then the compound becomes a chiral compound. Now my carbon, that is the one with 4 different groups attached to it, I am going to now draw my mirror image, because the 2 isomers are mirror images of each other. And so you'll notice that this carbon here is a carbon with 4 different groups attached to it. 1, 2, 3, 4. And so I write the mirror images. These are enantiomers, and they are optical isomers. All right, so if you want to identify which carbon in this compound is the chiral carbon, you'll see that this one is a chiral carbon right here. And so if we know that this one is a chiral carbon, you can identify it with an asterisk. So I have different groups attached to my chiral carbon. Now, what are those groups? This is one group. This is another group. This is a third group. And all of this is a fourth group. So the carbon with 4 different groups attached to it is the chiral carbon. And you now write the mirror images to show the 2 isomers, which are enantiomers. Part 4, state the color change observed when compound C in C1 reacts with bromine. Now let's take a look back at compound C in C part 1. Now if you notice that this is a carbon-carbon double bond. So if you're going to react Br2 with it, then you expect that Br would be added across the carbon-carbon double bond. And Br, which is bromine being red-brown, when it's added to compound C, it should decolorize when it forms Br across the carbon-carbon double bond. So the answer for part 4 that says state the color change observed when compound C in C part 1 reacts with bromine is a red-brown or orange-brown color to colorless. Part D. Observe the reaction scheme below and answer the questions that follow. Now, if you look at compound D, you'll notice that they have a carbon-carbon double bond here. So they show you that this group right here is an alkene group. You have an hydroxyl group here, and you have a carbonyl group here. Now, going from A to B, you'll notice that the carbon-carbon double bond group is what would have reacted with Br2, because there's no more C double bond group here, but you have a Br being attached across the carbon-carbon double bond. So if you're looking at compound A to B, then part 1 is bromine is being reacted with the carbon-carbon double bond. If you look at part B to C, you'll see that there is some form of oxidation taking place to go from the hydroxyl group to the carbonyl group. All right, so let's continue with part 1. Name the functional group highlighted in the compounds labeled A, B, and C in the scheme above. So compound A, that's your carbon-carbon double bond group. So for D, part 1, name the functional groups highlighted in the compounds labeled A, B, and C in the scheme above. Compound A, that's your carbon-carbon double bond, which of course is your alkene. For compound B, the group highlighted is the hydroxyl group. And for compound C, the group highlighted is the carbonyl group. Part 2, identify the reagents 1 and 2 in the scheme above. So for reagent 1, you notice that you need, of course, bromine, which is Br2 liquid, because if it's Br being added across here, it must be in the liquid state, which means that it requires a carrier. In this case, an organic solvent. You could use CCl4 or CHCl3. But if you simply say an organic solvent, you should be okay as well. For reagent 2, we did say going from B to C. For reagent 2, we did say going from B to C, it was oxidation because of the hydroxyl group changed to a carbonyl group. So you need an oxidizing agent. Now you could use acidified potassium manganate 7 or acidified potassium dichromate. Part 3, identify the color change observed when compound A is converted to compound B. So the color change, of course, you saw earlier that when you add bromine across a carbon-carbon double bond, you go from red-brown or orange-brown to colorless. Part 4, based on your response in D part 2, what color change is observed for the conversion of compound B to compound C? Let's have a look back at that. Now, if you look at compound B to C, we say the process is oxidation. And we did say you could use acidified potassium manganate 7 or acidified potassium dichromate. Now, if your answer is acidified potassium manganate 7, then your color change should be purple to colorless. If your answer is acidified potassium dichromate, then your answer should be orange to green. Part 5. Draw the structures of compound D and compound E in the space provided below. Now remember that if you are looking at compound D, let's go back so you can see what that is like. So compound D and compound E. Now what is happening here is nucleophilic addition, where you're adding H and CN minus across the carbon-carbon double bond to form an hydroxynitrile. That's compound D. So you see where we have back our BR, and we have CH3 here. And right here is where the HCN would be added. H to the oxygen and CN would be added to the positive carbon to get your hydroxynitrile. And for HBr here, you would add H and Br across the carbon-carbon double bond. However, the H, according to Markovnikov rule, must be added to the carbon with a higher number of H's, or the higher number of H in this case. So it will be added, the H will be added to this carbon and the Br to this carbon. Hence, you have this structure. So these are our structures where HCN was added across the carbonyl group to form your hydroxynitrile, and HBr was added across the carbon-carbon double bond, but the H must be added to the carbon with the higher number of H. And of course, Br will be added to the more stable carbon, or we could say the more stable carbocation. Name the reaction used to form compound E. So the name of the reaction is electrophilic addition, but they would accept also just saying addition reaction. Part 7. Give the reaction mechanism for each of the steps in going from compound A to compound E, using curved arrows to show the movement of electrons. So the first thing I want to say is that the movement of curved arrows, once you have your double barbed arrow, you are moving 2 electrons, right? So we are not moving 1 electron in any of these. So you won't see a single barbed arrow. So let's start with compound A. So compound A, we're going to add HBr across the carbon-carbon double bond, okay? So you'll see that this carbon, since HBr is already permanent dipole, right? So it has a permanent dipole. The H is positive, so the electrons from the carbon-carbon double bond would bond to the H, causing the bond between the H and the Br to break off, putting the electrons on the Br. So now we form Br minus, which is a nucleophile. So while this part is bonding to the H, the Br broke off, forming this nucleophile. This is going to attack the carbocation here, which is the stable carbon, and this one will form the Br, and we now have our compound E. So let's have a better look at that. So you will notice that I have H, Br here. And this, of course, is already positive, partially positive, and the Br is partially negative. So the electrons here would move to attach itself to this H to form the bond here. So I now have this is already there as my CH3. And now I attach this H here. And the Br, which comes off, is now a nucleophile. And now I formed a carbocation here. And so this Br would now attack the carbocation here to attach to this carbon, because you broke the carbon-carbon double bond here. So now I have my H there, my H3C, and my Br. And that is going from compound A to compound E. So this is the end of module 1, chemistry of carbon compounds.